Okay, I'm going to end up this series of videos here by just showing you a few more examples of solving systems of equations using this Gauss-Jordan method. So here we have a system of equations. We're going to start by writing the augmented matrix for the system. And that's going to look like 0, -7, +7, -21. 1, -2, 2, 1, 3, -6, 1, 8. Next, we need to get the reduced row echelon form of this matrix. There are multiple different ways you could do that. You could work it out yourself, performing the right sequence of those row operations. You could put the matrix into a graphing calculator and ask it to give you the reduced row echelon form. You could use one of the various apps or online tools or other software that will do things like that for you. So however you do it, when you get the reduced row echelon form, it turns out to look like this: 1007, 0102, 001, -1. And from that, we can tell that the solution to the system is x equals 7, y equals 2, and z equals -1. In other words, 7, 2, -1 is what makes all three of these equations true at the same time. Next example. For this system of equations, the augmented matrix is 1, 2, -3, -2, 3, -1, -2, 1, 2, 3, -5, -3. Then we get the reduced row echelon form of that matrix, and that turns out to be 1, 0, -1, 0, 0, 1, -1, -1, 0, 0, 0, 0. So here we have a dependent system. This is going to be one with multiple solutions. So if we translate the rows of this matrix back into equations, the top row is telling us that 1x plus 0y plus -1z equals 0. In other words, x minus z equals 0. And the second row is that y minus z equals -1. And the third row we can disregard because it's just all zeros. It's not really giving us any information. Now, when we have equations like this that have more than one variable in them, solve them for the first variable. So leave the x here, but add z to both sides, and we get x equals z. Leave the y here, but add z to both sides, and we get y equals -1 plus z, or z minus 1. So x and y both depend on z, and then z itself can be any number. So for x we have z, for y we have z minus 1, for z we have z itself. And so this is the pattern that all the solutions to the system have to fit. You can pick any number and put it in for z, and that gives you some particular triple that satisfies all three equations. So you could have 1, 0, 1, 2, 1, 2, 8, 7, 8, 100, 99, 100. Anything of that pattern should work in all three of these equations. And last example, x plus 2y equals 4, x minus 2y equals 0, 4x plus 3y equals 12. And here I'll just mention that we have three equations involving two variables. So if you want to visualize what's going on here, these three equations would represent three different straight lines. Now, when you have three straight lines, it's possible that all three of them intersect in one particular point. Like you could draw two lines, look at where they cross, and then draw a third line that also goes through that same point. But it's more likely that if you draw three lines, that they won't all three cross at the same point. So we might get a solution or we might not. Anyway, here's the augmented matrix: 1, 2, 4, 1, negative 2, 0, 4, 3, 12. Here's the reduced row echelon form of that matrix: 1, 0, 0, 0, 1, 0, 0, 0, 1. And what does it tell us? That bottom row is 0, 0, 1. Tells us there's no solution. The system is inconsistent. And before we leave this section, I will just mention that all the examples I've shown you have had just 3 equations and 3 variables maximum. But there's no reason you can't use this method to handle systems of 4 equations, or 5, or 10, or 100. It's the same approach, just lots more numbers, lots more rows and columns to your matrix.